Exercise questions of the chapter electric charges and fields. First questions. Two charges 2 into 10 power minus 7 coulomb and 3 into 10 power minus 7 coulomb placed 30 centimeter apart. What is the force between the charges? Force you can calculate using Coulomb's law. F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. Q1 Q2 by R square. Substitute the values and you get the answer. Ensure that the distance is converted into meter. Question 2. Electrostatic force on a small sphere of charge 0.4 microcoulomb due to another charge minus 0.8 microcoulomb in air is 0.2 Newton. What is the distance between two spheres? So again, you have to use the formula F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. Force is given in this case, so you can find the value of R from the equation. Cross multiply the equation, find the value of R in meter. What is the force on second sphere? Due to the first, the forces are equal and opposite, which was already proved. So the same 0. Newton force is acting there. Then question 3. Check that the ratio K E square over G ME MP is dimensionless. So here we can consider proton and electron of mass MP and ME separated by a distance R. Then the electrostatic force acting between them, Fe is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. Q1 and Q2 is equal to E in magnitude, so E square by R square, which can be written as a constant K into E square by R square. And the gravitational force between them, if G is equal to Newton's law of gravitation, we can apply G ME MP by R square. G ME MP by R square. Here you can take the ratio electrostatic force to gravitational force. Electrostatic force to gravitational force. So you will get the ratio K E square over G ME MP. Now, it is a ratio of forces Fe by Fg. So when you substitute the dimensions, you can show that, okay, being a ratio of the same quantity, the ratio is dimensionless. Now you can substitute the values of K, E square, G, ME and MP. And when you substitute, you will get an approximate answer around 10 power 39, this ratio. And it indicates that the electrostatic force between proton and electron is around 10 power 39 times the gravitational force between them. So the binding force between electron and proton in an atom is the electrostatic force of attraction, not the gravitational force. Now come to question 4. Explain the meaning of the statement. Electric charge of a body is quantized. We have seen already the total charge present in an object is an integral multiple of electronic charge, because we can have only the transfer of electrons between the bodies. Now, part 2b, why can one ignore quantization of electric charge when dealing with the macroscopic or large scale of charges? We know we need around 10 power 18 electrons to constitute 1 coulomb of charge. Very large amount of electrons, 10 power 18. Addition or removal of few electrons cannot make any difference in the total charge of a body. That is the reason for macroscopic system, quantization is not significant. Now, question 5. When a glass rod is rubbed with a silk cloth, charges appear on both. A similar phenomenon is observed with many other pairs of bodies. Explain how this observation is consistent with the law of conservation of charge. When we rub two objects, okay, the objects get charged. It is not due to the creation of any new charge, but it is due to the transfer of charge, more clearly transfer of electrons from one object to the other. So then what happened? We obtain only a transfer of charge, and the object which loses electron becomes positively charged, and the object which gains the electron becomes negatively charged, and it is consistent with the law of conservation of charge. Now, question 6. 4-point charges, magnitudes are given, okay, are located at the corners of a square ABCD of side 10 centimeter. What is the force on charge 1 coulomb placed at the center of the square? So we can first calculate what is the total electric field at point O. Here, two positive charges, 2 microcoulomb, and electric field is acting radially outward from positive charge. Being equal distance and magnitude, those two electric fields mutually cancel each other. And for negative charge, electric field is radially inward. They also mutually cancel each other. So the net electric field at this point E is equal to 0. The net electric field is 0. Therefore, when you place a test charge at point O, we have the equation F is equal to QE, as E is equal to 0, the net force is 0. Now, question 7. An electrostatic field line is continuous, that is, a field line cannot have sudden breaks. Why not? We know the electrostatic force is having infinite range. When R is equal to infinity, F is equal to 0. So when a charge moves in an electric field, it goes up to infinity. Therefore, electric field lines are continuous curves. The second charge is supposed to be at infinity. Then explain why two field lines never cross each other at any point. When they intersect, you can draw two tangents at the point of intersection, which represent the direction of electric field at that point. It is not possible to have two directions for one electric field at a point. Therefore, electric field lines cannot intersect. Next, question 8. 2-point charges, 3 microcoulomb and minus 3 microcoulomb, located 20 centimeter apart in vacuum. What is the electric field at the midpoint O of the line joining the two charges? So here you can see the total distance is given 20 centimeter. It will be two segments of 10 centimeter each. And the electric field due to positive charge is acting, EA is acting radially outward, while electric field due to negative charge, EB, acting towards it. And at point O, you can see both these fields are in the same direction. Therefore, the total electric field you can calculate E total at the point O is equal to EA plus EB is equal to 2EA we can take, because the charges are equal in magnitude. with the same distance. So is equal to 2 into 1 by 4 pi epsilon naught 1 by 4 pi epsilon naught q divided by r square. The value of r you have to take as 0.1 meter, and that much Newton per coulomb is the answer. Then if a negative test charge of magnitude 1.5 into 10 power minus 9 coulomb is placed at this point, what is the force experienced by the test charge? Again, you have to take F is equal to test charge Q into E total. That means the electric field at point O. So you will get the value of force acting on the charge. Now, question 9. A system has two charges, QA and QB, okay, equal and opposite, located at points 0, 0, minus 15 and 0, 0, plus 15 respectively. What are the total charge and electric dipole moment of the system? So, 0, 0, minus 15 and 0, 0, plus 15 means you can see those charges are placed symmetrically over Z axis, so that the distance between two charges is 30 centimeter. So it's an arrangement of electric dipole, and total charge of an electric dipole Q is equal to 0 because equal and opposite charges. Q is equal to 0, and dipole moment you can calculate using the formula P is equal to 2AQ, and 2A is equal to 0.3 meter. Substitute the values and you will get the answer in coulomb meter. Next, question 10. An electric dipole with dipole moment 4 into 10 power minus 9 coulomb meter is aligned at 30 degree with the direction of uniform electric field of magnitude 5 into 10 power 4 Newton per coulomb. Calculate the magnitude of the torque acting on the dipole. Torque formula is torque is equal to P sin theta. Dipole moment is given, electric field and angle are given. So you can substitute the values, find the answer in Newton meter. Question 11. A polythene piece wrapped with wool is found to have a negative charge of 3 into 10 power minus 7 coulomb. Estimate the number of electron transferred from which to which. The polythene piece gets negatively charged. Therefore, we can conclude electrons are transferred from wool to polythene piece. And the number of electron transfers, we have the formula Q is equal to Ne, or N is equal to Q by E. Is there a transfer of mass from wool to polythene? Of course, there is a transfer of mass as the electrons are transferred. But the mass of electrons are in the order of 10 power minus 31 kilogram is very negligible. So very negligible amount of mass only transferred. We can calculate that total mass transferred M is equal to number of electrons into mass of one electron. That will be the total amount of mass transferred from wool to polythene. Next, question 12. Two insulated charged copper spheres A and B have their centers separated by a distance of 50 centimeter. What is the mutual force of electrostatic repulsion if the charges on each sphere is 6.5 into 10 power minus 7 coulomb? The radii of A and B are negligible compared to the distance of separation. The radii are negligible means those two spheres can be considered as point charges. So accordingly, you will get the equation for force. Force is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. And here values of Q1 and Q2 both are same only. So Q1 Q2 by R square, substitute the values, so you will get the answer. Now, what is the force of repulsion if the sphere is charged double the amount, that means q becomes 2q and the distance between them is halved, r becomes r by 2. So in this case we can calculate force F1 is equal to 1 by 4 pi epsilon naught 2q1 into 2q2 divided by r by 2 the whole square. It becomes 1 by 4 pi epsilon naught q1 q2 by r square into 16. Therefore we can conclude F1 is equal to 16 times F, and substitute the value of F and find the value of F1. Now question 13, suppose the spheres A and B, the previous question, have identical sizes. A third sphere of same size but uncharged is brought in contact with the first, then brought in contact with the second, and finally removed from both. What is the new force of repulsion between A and B? So this condition is applicable for identical spheres only. So we have sphere A and B, both are carrying charge Q. Now an identical sphere C is in contact with the A. So what happens? The charge of A, they share the charge equally. So both are having charge Q by 2 now. Then the sphere C, now carrying charge Q by 2, is made in contact with the sphere B, which carries charge Q. So then what happens? They share the charges equally. So Q by 2 plus Q is the total charge, divided by 2 will be the charge for each sphere. That means you will get 3Q by 4 is the charge of each sphere. Means the charge of B now becomes 3Q by 4. Therefore, now the force F2 is equal to 1 by 4 pi epsilon naught. The first sphere A is having charge Q by 2 into sphere B is having charge 3Q by 4 separated by distance R is equal to 3 by 8 into 1 by 4 pi epsilon naught Q1 Q2 by R square. It will be equal to 3 by 8 times the initial force F. Now, question 14. Figure shows tracks of 3 charged particles in uniform electrostatic field. Give the signs of 3 charges. Which particle has the highest charge to mass ratio? And you know that when you have a positive plate and negative plate, a uniform electric field is acting from positive plate to negative plate. So uniform electric field. And the positive charge experiences force in the direction of electric field, while negative charge experiences force opposite to the direction of electric field. Here you can see charge 3 experiences force in the direction of electric field. Therefore, charge 3 is a positive charge, while charge 1 is having force opposite to electric field, same as for charge 2 also. So we can see as the force is opposite to the direction of electric field, 1 and 2 are negative charges. Now next, we need to calculate which particle has the highest charge to mass ratio. So you can see initially all three charges are traveling along positive x-axis. They got a deflection along y-axis due to the force applied by electric field. And the force applied by the electric field, we have F is equal to QE, or we can say MA is equal to QE, or acceleration due to electric field, A is equal to QE by M. Now, as the particle has got a deflection along y-axis, we can write the equation for motion along y-axis. Y is equal to UIT plus half AY T square. UIT plus half AY T square. Now, initially all the particle travels only along x-axis. So, value of Uy is 0. And we can substitute the value of Ay, which is QE by M into T square. Therefore, for the motion of the particle, you will get a y is equal to QE T square by 2M. For a given particle, we can see Q, E and M are constants. Therefore, we can say y proportional to T square, a second degree equation. So we can conclude, in the presence of electric field, a charge follows parabolic path. That is a conclusion from the equation. The nature of path followed by a charge in an electric field is parabolic. Now, come to the question. There are three particles having different values of Q and M. So, at a given time t, we can write y proportional to Q by M, which means the particle having maximum deflection along y-axis will have the maximum charge to mass ratio. So there, approximately we can find out here the first particle. So like this, you can see a deflection along y-axis like this. And for the second particle, having a corresponding deflection, while the third particle having deflection like this, so that we can conclude almost the third particle having maximum value of y. Y is maximum for particle 3. Therefore, particle 3 is having maximum charge to mass ratio, which we call the name specific charge. For electrons, we say it is E by M of electrons, etc. Next, question 15. We have a uniform electric field. E is equal to 3 into 10 power 3 I cap Newton per coulomb, which means the electric field is acting along positive x-axis. What is the flux of this field through a square of 10 centimeter on a side whose plane is parallel to YZ plane? So here we can have x-axis, then electric field is acting along x-axis. So y-axis and z-axis, and here you can see the electric field is perpendicular to the square. So we can have the square here, square area, and you can see the direction of this area you will get by drawing a normal outward. So n cap represents the direction of area. And accordingly, electric field and the direction of area both are same. And you have to calculate phi is equal to E dot ds. Here E and ds are in the same direction. So you will get E ds and substitute the value of E and ds. Ds you have to take the area and find the value of flux Newton per coulomb per meter square. Okay, now meter square, not per meter. Next, what is the flux through the same square? If the normal to its plane makes a 60-degree angle with the x-axis, then value of flux phi will be E ds cos 60 will be the value of flux. Next, what is the net flux of uniform electric field? In the previous question, through a cube of side 20 centimeter oriented so that its faces are parallel to the coordinate planes. Okay, so here when the faces are parallel to the coordinate plane, you will get here a box. And the electric field is along positive x-axis. And see what happens there. So electric field is acting like this. Now here electric field is entering into this phase, field lines, while field lines are leaving from this phase. So number of field lines entering in the left phase is equal to number of field lines leaving the right phase, so that the net flux is equal to 0. Then next, a careful measurement of the electric field at the surface of a black box indicates that the net outward flux through the surface of the box is 8 into 10 power 3 Newton meter square per coulomb. Flux is given. What is the net charge inside the box? So net charge Q is equal to, we can apply Gauss law, Q is equal to phi into epsilon naught. You will get a net charge. And if the net outward flux through the surface of the box were 0, could you conclude that there were no charge inside the box? Why or why not? So again, we can have a box and no flux is entering or emerging from the box. Okay, does it mean that there is no charge inside the box? It's not necessary. Suppose we have a charge, negative Q and positive Q here. Now we know electric field lines originate from positive charge and terminate at negative charge. So no field lines can emerge out of the box. So you can see there the charges are present, but net charge is equal to 0. Net charge is 0. So the charges may be present inside the box, though there is no flux through the box. The charges may be present inside the box, but net charge is equal to 0. That's the only condition required here. Now question 18. A point charge 10 microcoulomb is a distance of 5 centimeter directly above the center of a square of side 10 centimeter. What is the magnitude of electric flux through the square? Okay, so here in this case, we can just assume a small box and of side 10 centimeter. Box like this we can consider. Now the charge is placed 5 centimeter from the surface. This is 5 centimeter. Now accordingly, okay, when we imagine the box like this, then we can see the charge is placed at the center. Charge Q is placed at the center of the box. And the total flux emerging out from the box we can calculate applying Gauss law. Phi is equal to Q by epsilon naught. But this flux is emerging out through all the 6 faces of the box. We are asked to calculate only the flux passing through the base area. So in such a situation, the flux passing through the base area, okay, phi dash is equal to total flux divided by 6. Therefore, phi dash is equal to Q divided by 6 epsilon naught, and you can substitute the values, so you will get the value of phi dash. Next, question 19. A point charge 2 microcoulomb is at the center of a cubic Gaussian surface of 9 centimeter on edge. What is the net flux through the surface? Whatever be the nature of the Gaussian surface, flux phi is equal to Q divided by epsilon naught. Then next, a point charge causes an electric flux of negative 1 into 10 power 3 Newton meter square per coulomb to pass through a spherical Gaussian surface of 10 centimeter radius centered on the charge. If the radius of the Gaussian surface were doubled, how much flux would pass through the surface? And what is the value of point charge? So here we can consider a Gaussian surface. Okay, the charge Q is placed there, and the flux will come out like this. Field lines will emerge in this way. So here it is negative, so the flux is entering into the surface. Now the radius is doubled. When the radius is doubled, you can see like this another Gaussian surface, and also you can see the same amount of flux is entering into the surface. So here same amount of flux entering the surface. Okay, the value of the flux will be same, that is negative 1 into 10 power 3 Newton meter square per coulomb. Then what is the value of point charge? Again, you can calculate Q is equal to epsilon naught into phi. Next, question 21. A conducting sphere of radius 10 centimeter has an unknown charge. The electric field 20 centimeter from the center of the sphere is 1.5 into 10 power 3 Newton per coulomb and points radially inward. What is a net charge? So electric field is given. Okay, electric field due to the charge is given. So electric field due to point charge, our formula is E is equal to 1 by 4 pi epsilon naught Q divided by R square. You can cross multiply the equation for Q and find its value. Remember, the value of Q will be negative because the question says the field lines points radially inward. So Q is negative. You have to give a negative sign to the final answer. Question 22. A uniformly charged conducting sphere of 2.4 meter diameter has a surface charge density of 80 microcoulomb per meter square. Find the charge on the sphere and what is the total electric flux leaving the surface of the sphere. We have surface charge density sigma is equal to Q divided by A. Now you have to find the value of Q is equal to sigma A is equal to sigma into it's a sphere, so 4 pi r square. Substitute the values, you will get the answer. Now, what is the total flux passing through the surface? Phi is equal to, according to Gauss law, Q divided by epsilon naught. Question 23. An infinite line charge produces a field of 9 into 10 power 4 Newton per coulomb at a distance of 2 centimeter. Value of R is 2 centimeter. Calculate the linear charge density. Electric field due to an infinite line of charge E is equal to 4 pi epsilon naught 2 lambda by R. Cross multiply the equation and find the value of lambda. Next question 24. Two large thin metal plates are parallel and close to each other. On their inner surfaces, the plates have surface charge densities of opposite sign and magnitude 17 into 10 power minus 22 coulomb per meter square. Okay, so they are having surface charge densities opposite sides, which means here one of the plates positively charged while the other one negatively charged. The same surface charge density. Okay, now we can take in region 1. When you take region 1, electric field due to positive charge is radially outward and its formula is sigma divided by 2 epsilon naught. And electric field due to negative charge is towards negative charge and its formula is again sigma divided by 2 epsilon naught. So the total field in region 1, E1, is equal to 0. Those two fields are mutually cancelled. The same thing you can see for region 3 also. The electric field due to positive charge is normally outward, sigma divided by 2 epsilon naught. Due to negative charge, plate B is inward, sigma divided by 2 epsilon naught. And the total electric field in region 3 is also is equal to 0. Now you take region 2. Region 2 you can see electric field due to positive charge is radially outward, sigma divided by 2 epsilon naught. And electric field due to the negative plate is towards the negative plate and its value is sigma divided by 2 epsilon naught. So you can see in region 2, both the electric fields are acting in the same direction in region 2. That is sigma divided by 2 epsilon naught plus sigma divided by 2 epsilon naught as they are in the same direction. So you will get sigma divided by epsilon naught. Can substitute the values and find the value of electric field in between the plates.